A very good morning to all of you. Welcome to this class, Fluid Mechanics and Hydraulic Machines. Today we are going to discuss about the Bernoulli's equation, Bernoulli's theorem. So before going to the Bernoulli's theorem, there is the basic principles of the fluid flow. What are those? Continuity equation, energy equation, momentum equation. Continuity equation is based on the conservation of mass, energy equation that is based on the conservation of energy, and momentum equation is based on the conservation of momentum. So generally these three equations required to govern the fluid flow. In this session we will mainly focus on the Bernoulli's equation, which is based on the energy equation or energy conservation. So let's first see the continuity equation. What is the continuity equation? The equation based on the principle of conservation of mass is called the continuity equation. Here is the conservation of mass. Conservation of mass, that means the total fluid mass, quantity of the fluid, that is the mass per second per unit time, is constant at all the cross section in case of the pipe flow or open channel flow. So that means the quantity of the fluid flowing per unit time is constant. If you say the quantity of the fluid, that is the mass per unit time, that means the you can see mass per unit time, it should be the constant. So mass, how you can write the mass? Volume into density by time, volume into density by time. So that we can further write volume upon density. Volume we can write the, here I am writing, see, m upon t, that is equal to volume, mass, volume into density per unit time. Volume we can write area into length, density by time. This length upon time, that can be written as the velocity, area into velocity into density. So this quantity should be constant as per the conservation of mass, that is the continuity equation. So for the compressible fluid, at section 1, mass per unit time, that should be equal to at section 2. So mass per unit time, that means the rho A into V. So at section 1, rho 1 A1 V1 should be equal to rho 2 A2 V2. In case of the incompressible fluid, density will become equal, that is for this incompressible fluid, density rho 1 is equal to rho 2. So here rho 1 and rho 2 will cancel out and A1 V1 equal to A2 V2 will come out. So that is the continuity equation. Now we are moving to the next one. This is just one example is given in terms of problem for the continuity equation. This is the pipe. Pipe is given, here the diameter of the pipe is 0.1 meter given and velocity at this section is given 5 meter per second. This is the section 2, here the diameter is given 0.15 meter and you have to find out the velocity. So at section 1, suppose section 1, this is section 2. At section 1 and section 2, as per the conservation of mass, continuity equation we can apply. So here you can write the A1 V1 equal to A2 V2, that is the continuity equation. So you know A1, this is the pipe. So pipe area you can write the pi by 4 d1 square into V1, that is equal to pi by 4 d2 square into V2. D1 is given here 0.1 meter, V1 is given 5 meter per second, D2 is given 0.15 meter. So you can find the V2, only one unknown parameter. So you can find here the V2, how much it is coming. So based on the continuity equation you can solve the problem. Next, one more problem you will see. This is the pipe, main pipe, that is divided into the flow is coming. It is divided into the two branches. In the main branch, velocity and diameter of the pipe is given. velocity 2.5 meter per second, diameter is 0.3 meter. In section here is divided into the two other sections. In the this is suppose section 1 main branch, section 2 sub branch, section 3 is the sub branch. In section 2 velocity is given 2 meter per second and diameter is 0.2 meter. While in the section 3 diameter is 0.15 meter and velocity you have to find out. So here the diameter is changing and you have to find the velocity in this pipeline in the sub branch. So whatever the flow is coming, it is going to be divided into the two sections. So total discharge Q, that is should be equal to Q1 equal to Q2 plus Q3. Q1 is the discharge in the main pipe, Q2 in the sub pipe and Q3 in the sub pipe. You can write the continuity equation, that is A1 V1 that is equal to A2 V2 plus A3 V3. Here diameter is given for all the three pipes, so A1, A2 and A3 is known. You can write A equal to pi by 4 d square. So corresponding to 1, 2 and 3, it can be written as diameter D1, D2 and D3. So you will get the A1, A2 and A3. Velocity V1 is given, V2 is also given, V3 you have to find. So only one unknown parameter is there that can be find out from here by putting all the values. So this is also based on the continuity equation. Momentum equation, that is the conservation of momentum. Momentum equation is based on the conservation of momentum or the momentum principle. What is this momentum principle? It states that the net force acting on the fluid mass is equal to the change in the momentum of flow per unit time in that direction. That means net force acting on the fluid mass, that should be equal to the change in the momentum of flow per unit time in the same direction. That is the momentum equation which is based on the conservation of momentum. This momentum equation, this momentum principle we will deal in some other section. In the today's section we are going to mainly focus on the Bernoulli, that is the conservation of energy. So we are going to the next one, that is the momentum equation. This is given just for the view what is the momentum equation or momentum principle. Energy equation, it is based on the conservation of energy. It states the law of conservation of energy states that the energy can neither be created nor be destroyed. It can only change the forms. If total energy is the sum of the, suppose total energy is the sum of the kinetic energy and potential energy. So if one energy is reducing, other energy may increase. So that is the sum will become constant total energy. That is the energy equation, conservation of energy. Now coming to the Bernoulli equation. Bernoulli equation is based on the conservation of energy. What it states? It states that in a steady flow, the sum of all forms of energy in a fluid flowing along a streamline is the same at all points on that streamline. Suppose a streamline is there in the steady flow. So number of points are there in the streamline. So at all points, the total energy will become equal to constant. At all points, if you compute the total energy at all the points, it should be same. That is the Bernoulli equation. That is the form of the energy may change. So the total energy in that, whatever the energy will be there, that may be changed. Their value may change, but the total energy will be same at all the points in that streamline. Total energy is the sum of the kinetic energy, potential energy and the pressure energy. So we can write, you can see here, in the total energy can be written as the potential energy, kinetic energy and the pressure energy. So this total energy, before going to all these three forms, this total energy can be written in terms of the head. It's difficult to measure the energy in the lab while you are doing the experiment. It is difficult to measure the energy. So energy is measured in terms of the head. Head can be measured easily. So how to convert the energy into the energy head? So here energy head is there. You can see energy head. That is the energy is written in terms of the energy head. So this energy can be represented in terms of the head in the fluid flow. So this energy per unit weight is called the energy head or head simply. The energy per unit weight of the fluid is the energy head or simply head. So that means as per the Bernoulli's theorem, total energy is constant, so total energy head will also be the constant, as the simply energy is converted into the energy head. Energy is written in terms of the energy head. How to write the energy in terms of energy head? So energy per unit weight of the fluid. We will see all this, how we can write the kinetic energy in terms of the kinetic energy head, potential energy into the potential energy head, and the pressure energy into the pressure energy head. So here total energy head is the potential head, pressure head, and kinetic head. So this potential head can be written as Z, pressure head can be written as P upon gamma, and kinetic head can be written as V square upon 2G in case of the no head loss. We will see later on this one. So total energy, that is the potential head, total energy head, that is equal to potential head, pressure head, and kinetic head. This potential head Z, P upon gamma, pressure head, and kinetic head is the V square upon 2G. So total energy will be constant at section 1 and at section 2. So this is can be written as at section 1 and section 2. That is the Z1 plus P1 upon gamma plus V1 square upon 2G, that is equal to Z2 at section 2 plus P2 upon gamma plus V2 square upon 2G. Now we will see this is the Bernoulli's equation in terms of the head. Now we will see each term separately. Potential energy head. Potential energy head, that is potential energy, if you say potential energy, that is equal to mgz or mgs, sometimes it is used the symbol in place of the z. So that is the potential energy. Now the potential energy head, so it is what? Potential energy per unit weight of the fluid, weight of the fluid. So potential energy is mgz. What is the weight of the fluid? Weight m, weight of the fluid is mg, m into g. So you can write m into g, potential of, that is the weight of the fluid. So mg will be cancelled, that only z will remain. So this z is the potential head. Now similarly, this is the elevation from the reference line. If the pipeline or open channel flow is there, so we have take the reference line. From the reference line up to what level the z value is there. Simply it is the elevation value. So that is the potential energy head z simply. Now kinetic energy head. So what is the kinetic energy? You can write the kinetic energy half mv square, and kinetic energy head, how you can write? That is equal to half mv square kinetic energy divided by the weight of the fluid mg. So mm will cancel out and v square upon 2g will remain. So this v square upon 2g is the kinetic head is called, where v is the flow velocity and g is the acceleration due to gravity. That is the kinetic head. Pressure energy head. Pressure energy, what we can write? The pressure energy, we can write the pressure into volume, that is the pressure energy. Now the pressure energy head, we can write PV upon weight of the fluid mg, right? Now how you can write this? This is mass. Mass can be written as P into volume. Mass can be written as volume into density. G is there. So this volume will cancel out, and what will remain? P upon rho g. So this, that is equal to P upon rho g, and this P upon rho g is also called the P upon, you can write P upon gamma. Rho g is equal to, that is gamma equal to rho g. So P upon gamma, that is the pressure energy head, simply pressure head. So in this way you can find out the all this head. So total energy head, simply we can write potential head plus pressure head plus kinetic head. So Z is the potential head, P upon gamma, that is the pressure head, and kinetic head is the V square upon 2G. sometimes the head losses is there. So in that case it can be written as head loss can be added. So Z plus P upon gamma plus V square upon 2G plus HF, where HF is the head loss. So that is the total energy. In terms of total energy head, you can convert the total head into the energy by multiplying the weight of the fluid. If you know, suppose you know the head, total head, if you know the total energy head, then multiplied by the weight of the fluid, you will get the total energy. That means head is easy to measure, that's why it is measured, it is energy is represented in terms of the head. So this is how we can write the Bernoulli's equation. Thank you for this session. Thank you.